was gonna collect Jenny's data from Total Fit yesterday. She did fitness testing. I'm gonna ask her to give me all like the push-up numbers and get a graph for you guys and see, well, what's the average number of push-ups? Should we use the average if it can be? What's the standard deviation? So see if we get some outliers that way. She's still collecting when I left class. Yeah, it would be. It would be. Plus a pre-post to see if there's a difference after week 8 versus week 2. So there's all kinds of ways to use this.
Within males and females.
Sure, break it down by gender, break it down by age, break it down by how many terms you take in the course. I mean, there's all kinds of neat little conditionals. Speaking of conditional probabilities, neat little conditionals you can place on the data to see what there is to see.
How long they eat.
Sure, sure. So essentially, this is a really cool way of being able to analyze data that looks like this. Beautifully symmetric-ish, enough-ish. Not to use ish twice. But when your data does have that kind of bell shape to it, this gives you a quantifiable way of discussing what that number means. I love the number S. I love what S stands for, but when you're first learning statistics, it's like, okay, I got it. It's the average distance. But how can I use that? Well, then, this is, again, why I was talking about those tires. If you're making a decision based on this, the tires most likely are going to follow a similar kind of shape. So what you can end up having is, let's draw a picture over here. What you can end up having with the example that I gave you before, so suppose here's the maximum lifespan of a tire. Okay, and it's down here at, let's say what did I say, it was 40 and 38, and plus or minus 10 and plus or minus 2. Yeah. So we'll just make this be 30,000, I think, and this be 50,000. And when I say that, you know, the standard deviation of the first curve was 10,000, right, or was 10,000, yeah, 40,000 plus or minus 10, well, that curve for that graph might look like this. So 68% of the tires are going to fall here. You're going to have 17% here and 17% here. The other brand, I'm not going to draw on the wall, this building's too new, but here's 40,000. The other brand has an average of 38,000, but because its standard deviation is only 2,000 miles, it's going to look like this. And it's going to go much higher than that. Okay? So the idea is you've got more of a chance of getting, yeah, some good highs, but also some good lows. So they cancel an average to 40, but because of that wide spread in the data, you might be getting you're taking more of a chance with the average of 40,000 than the average of 38,000, which is way more consistent as far as what you're getting. And that depends what kind of person you are. I mean, you might say, roll the dice, let's see what I get. Okay, go for it. I mean, that's sometimes that, you know, you can do that. But if you're going for consistency, you want to get brand with a smaller standard deviation. If you can even find that data from people. That's the trick. What is the plus or minus? And most people don't understand what that means. They don't understand it. They understand an average, but they have no idea what standard deviation is. So, is that fair? Ish? Fair-ish. Good. So, we know what the standard deviation is. We know how to do a number of standard deviations. You're not limited to 1, 2, and 3. You can have 4, you can have 5, you can have 0.7. We'll get more into that too as we go through the course. So you don't have to have an integral number of them. Yeah? Good? Okay, that's 90% of what I want to talk to you about today. I mean, literally 90%. The only other thing I want to chit-chat about is a technical. It's a technical. It's what if you don't have raw data? So everything we just talked about applies to what we're about to talk about now with this last 10% of class, really, honestly. The difference is it's a technicality of when you're not given raw data. How can you process grouped data or data given to you in a frequency distribution? So, look at the next data set on that data sheet. This is some data I collected a couple of years back. I should update the marathon. I think I will do that over the summer. Did anybody, speaking of marathons, anybody hear what happened with the bombs at Boston?
How can you not?
Well, I mean, have they figured out what happened? Like what?
They found a backpack with pressure cooker.
A backpack with some stuff.
Yeah,
Okay.
that's what I heard earlier this morning.
Okay. Pressure cookers.
They were inside first.
Yeah.
So designed to make a mess, basically. Designed to make a mess.
Yeah, Facebook's covered in pictures about people with. Yeah.
I know.
Really?
One of the problems is.
friends.
What's that?
She's just saying she has pictures, and I'm like, I haven't seen one, so.
Yeah, exactly. Yeah. That's one of the. it's a good thing and it's a bad thing with having everybody with little cameras walking around. It can be good, it can be bad, yeah, so, anyway. I mean, I think in a lot of ways it helps gonna help with law enforcement, it'll help in a lot of ways, and who knows, maybe somebody got a picture of something that'll help crack this, hopefully, once they process the terabytes of data that's out there, but anyway, sorry, didn't mean to bring it all down right there. So anyway, here are some new data to play with. I'm gonna go ahead, if you guys don't mind, and erase this, is that cool? Because we're gonna start from scratch here, so we'll go with the Portland Marathon data. And remember, I'm not ignoring the median and the mode because they're not nice. I'm ignoring the median and the mode for two reasons right now. Number one, it's symmetric bell-shaped data. So the median and the mode are essentially the same as the average. We might as well talk about just one. And the reason that we're talking about the average is because the sample standard deviation is based on the average. There is no measure of deviation that we need to talk about in this class that's based on the other ones. So, let us not worry about those. Take this out of here. Goodness gracious. So what I want to do, and you guys know how to deal with this already in some ways. If I asked you to find the average age of a runner in the Portland Marathon based on this data, you could do it right now. You could do it right now. So I'm gonna put the distribution up here on the board. So X is age, F is frequency, and I'm going to leave one number in between here, obviously. So we've got 17 to 26, we've got 27 to 36, 37 to 46. What kind of data is this?
It's continuing.
It sure is, isn't it? Because it's based on age, which is based on, at the end of the day,
Time.
time. At the end of the day, it's based on time.
Also, this is.
Like, I know this one, time.
We're talking about groups.
Totally, it's grouped. It's totally grouped. And the groups,
It now.
this column is very important over here. This frequency column, 44, 107, 141, 106, 46, and 4. Let's play in the home game. Here's your data set. Actually, I should go this way. Or just link to cocc.edu/srule. Why is the frequency column important?
So that you know how many times it's occurred.
Right. Otherwise, if you don't have the frequency column, what's the assumption?
Everyone's the same age, or everyone goes at the same.
There's one person in each of those ages. You got it, Robin. If there's no frequency column, you have no idea how many 17 to 26-year-olds there are. You have no idea how many 27 to 36-year-olds there are, so you assume there's one of each. And there's the only assumption you can make. You can't just create data. So the frequency column tells you. It's basically like your GPA for ages. It's your grade point average, but we're not talking about how you're doing in school. We're talking about how old these runners are. So the data we're interested in is the age of a Portland Marathon runner, the typical age of a Portland Marathon runner. Cool? All right. It's typical, usual, balanced, whatever word you want. Shared. If they were all the same age and we still have the same number of people, what would that average age be? So, what's the first thing you have to do? As a matter of fact, you should probably take this away and put it here instead. What's the first thing you have to do? Exactly. Find the, if you will, the class mark or the median age for each one.
Yeah.
So we don't know how many are 17, how many are 18, how many are 19. So call them all.
21
I think 21's in the middle, isn't it? The lights just went down again.
21 and a half.
This is going to be 31, I think.
Do you want to do like halves and stuff?
Should we? Hang on a second. What's the average of 17 and 26?
I thought it was 21 and a half.
It's 21 and a half. It is. I think you're right, Haley. These should be half, shouldn't they? Yes, it's a point. Good, and we should. Why should we use the halves?
Because it's the exact middle.
And why is that important? Yes, Rachel, that's 100% correct. Why is that important to use the exact middle?
Precise value.
Yes, if we use 21, 31, 41, we're going to be underestimating on average. Because we're calling everybody a half year younger. And it doesn't seem like that big of a deal until you apply it to hundreds of people. Then you've got a half a year offness, if you will, across the entire data set. Yeah, so use the exact middle, get as much precision as you can. 51.5, 61.5, and 71.5. Thank you, Haley, for catching that. I didn't need it. This is why, check my arithmetic, friends. Check my arithmetic. It's usually pretty bad. So essentially, this is your new data set. We no longer have 44 17 through 26-year-olds. We now have 44 21 and a half-year-olds.
Right.
We now have 107 31.5-year-olds. We have 141 41, and so forth and so on. It's the same thing you do in your quiz for this week, with the times for the Niagara, for the Old Faithful eruptions. Cool? Now, what you did before, for like Old Faithful, for example, was you created an X times F column. We're done doing that. We're going to use 2 lists in your TI, and let the TI do it for us. Yes, this is why we have technology, because technology is wonderful. So, go back into your data list, clear out L1, replace L1 with this guy here, clear out L2, and replace L2 with your frequency list. Yes, this is our friend. This is our friend. Yes. I like making you guys do stuff by hand until I feel you've kind of gotten a feel for what the hell's going on. And then I don't have to test that feel anymore, because the feel becomes, if you will, kind of automated. So stat, edit, you guys are already ahead of me. Good for you. And you just use list 1 and list 2, Rach. And you'll see a similarity with what we have to do in the 83 and 84, and what you're doing over there. And 71, 45, and the frequencies. Oops. Cool. Let's make a graph of this first. It's a little silly, because essentially you're graphing 6 data points, each a numbers of times, but let's get you in the habit of being able to graph grouped data like this. So the way you do it, the same way you did before. Second, y equals. That's exactly the same. So Rach, you're going to have to go to stat apps, plot setup, whatever it's called. Plot 1, just like before. So number 1, plot 1. Everything's the same except for what? What do you think?
The frequency.
That's the only thing. Your frequency. No, your type's still going to be a histogram. We're still going to make a histogram? Absolutely, yeah. We're going to stick with histograms for right now. We'll add other stuff as we need it. I'm thinking next class we'll have what's called a box and whisker, which is a fun little guy to play with. We're going to scroll down to frequency, because your frequency is no longer 1. Your frequency is what's in list 2, L2. So you want to put second 2, not 5, second 2, oh God, hang on. Second 2 there. Yeah, if you leave it at 1, it's going to assume that you have one 21.5-year-old, one 31.5-year-old, one, and you don't have that. You've got more in the middle than you do on the ends. So you want to make sure that your data represents that. Your data stands for that. Is that fair? Believable? Now, zoom 9 gets you a graph again. Zoom 9 gets you a graph. Zoom 9. There she is. It looks a little weird. It's a little spaced because of the fact that and you can finagle that. You can finagle with that to change. If you want the bars to touch, you can actually get in there. And I'm not that worried about it. I'm not that concerned. So would you call that bell-shaped data?
Yeah.
It's almost perfectly bell-shaped data. Notice these guys over here? They might be outliers. They might be outliers. Maybe these two, but that bar is so high I doubt it. So why don't we test out our newfound skills of standard deviation analysis and go out 1 and 2 standard deviations for this Portland Marathon data and see if we can apply it to that graph. So now we're going Portland Marathon. Portland Marathon data. And let's just get 2 numbers. Let's get the average age and the standard deviation of the ages.
46.5 and 18.7.
Jordan is one step ahead of me, obviously. So, first of all, we have to run one of our stats to get this. But there's one adjustment we have to make, right, Jordan? And you've obviously made it. So everybody, back to your stat screen. Go to Calc Next, just like we did. Enter. Now, do not press Enter again right now. Well, what the hell? I will. You don't. If I press Enter, not that. If I press Enter right now, it's going to give me numbers. It's going to say the average is 46.5 and the standard is 18.7. But what's the problem with that, Jordan?
Let's do L1 and L2.
Right, are there only 6 people in my sample? No, there's a few hundred in my sample. But the TI doesn't know that because when you just press one of our stats, it only looks where?
L1.
L1. So you have to tell it. So I want to hit clear here. Go back to stat calc, one bar stats, and here's where you put L1, second one, comma, L2. What this will do, it's essentially doing the same thing that when you set the graph up. When you set the graph up and you had to put xlist L1 freak L2, it's doing the same thing. But this is how you do it on the home screen. Now press enter. Now press enter.
It should be right above 7.
Say that again?
The comma.
Oh, the commas, yes, it's got its own button, Elena, in terms of, it's right above 7, it's right here.
And you'll always tell us what you want us to round to, right?
Exactly. Let's do the same thing with the last. Let's round to the nearest whole number.
Okay.
Nearest whole number again. So we've got 42 years for an average age, plus or minus about 12 years for a standard deviation of ages. Ish. So based on the fact that data is roughly bell-shaped, we can use this cool empirical rule to talk about percentages of the people in the race. So for example, roughly 2/3 of the data are going to be, or roughly 2/3 of the runners are going to be about how old to how old? About 2/3, 42 years, 12 years. So about 2/3 of the runners are going to be at least how old?
30.
About 30, or at most 54. That's within one standard deviation, 2/3 of the data. So if we take 12 away from 42, that's 30 years. And if we add 12 to 42, that's about 54 years. So there's about 2/3 of the data. How about 95% of the data is going to be between, we go down 24 from 42, it's at 18. And if we go up 24 from 42, we get 66. There's about 95%. And that makes sense because now we're getting into the remainders are these guys here and these guys here. The problem with grouped data is we can't do that cool little fine-tooth comb analysis we did with the weight loss data. We can't go into the actual data set and go, oh. So when I say, for example, that 2/3 of the data are from 30 years up to 54 years, I lose a little bit of that, because where's 30? Well, 30's in here, but it's in there in the middle. So there are some of the members of this that are actually outside of that. Same thing with 54. 54 is up here. So there are some that are, yeah. So you've got some issues there. But that's okay. That's okay. Mainly, I just wanted to make sure you guys knew how to A, graph group data, and B, make sure you can calculate it properly. Look how many runners were actually in this data set. How many runners are actually in this data set? Right there. That's the sum of your L2. That's how you can check to make sure you did something correctly. If you were able to get not 6, chances are you did it correctly. Chances are you did it correctly. And there's nothing wrong with running it on 6. The problem is it ignores the frequencies, and you actually ignore the shape of what you had. You don't want a uniform distribution if you don't have one. Cool? Ish? Yeah. So the big takeaway, again, standard deviation is average distance from average, which is, we had that from last time. But now we picked up not only a graphical tool for creating these histograms, but we also picked up a bit of an interpretive tool that talks about how much data is within a certain range of values. That's good. That's actually quite good. We're not going to leave that alone. That's going to stay with us the rest of the course. It'll ramp up more towards the end, but it's a cool idea to kind of filter. How many of you have heard that 68, 95, 100% thing in psychology classes? Nobody. Okay. You eventually will. If you take a social class or a psych class, it'll pop up there too.
Oh, I have.
Oh, you have, yeah. Excellent. Usually 1 or 2 people in a classroom have. Okay, so let's cut this out. Thanks for playing.